number have a magnitude and phase. They do two different things of the signal to the output. The magnitude magnify and the phase delay. Okay, so that when you look at the filter, you can see what each component does. Alright, so that concept clear. Now, typically, what we do want to have, what we do want to have now here is understand the impact of this, because a signal can be decomposed into this component or this sinusoidal. So a typical filter, you want to do something like, okay, I want to pass a certain frequency. I want, for example, all the omega naught within certain range get through. That means I want to make those numbers big or small. That's where I need to. But associated with that, I have this shift. I got this shift. And that shift, this signal here, you can see this shifted here. This shifted here. When you want to write them, maybe I have to write y of n is equal to h of omega naught and then time cos. So I want to put out a cos function. So it can always write the cos function of omega naught, and then inside here I got n plus the phase of h of omega naught over omega naught. Okay, right? And now if this thing here equal to a constant, I assume I have this thing equal to a constant, let's say constant alpha here, for example. So if the magnitude of h of omega naught is equal to alpha omega naught, then what happened? The phase shift is constant for every frequency. Doesn't matter what omega naught is, it always shifted by the same amount. Right? Now what happens if that's not the case? If that is not the case, then for different frequency, it got shifted differently. And that would be very deadly, because let's say I play music here, like boom, 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 so different frequency play different time. I pass through a filter, right? Design a really good filter. I go over here, different boom, boom, boom in different frequency. Now they will all mix up, right? And then you got very distorted music. Can you see that, right? Because we learned yesterday, the content in the speech or the voice signal is time and frequency. Right? I say certain words at certain time. Now I got a filter. You design a filter for a cell phone system. The person down and hear exactly the same frequency, but now mix up. So it could say word by word and so on. Right? So is that clear? So the message here is, if you have a filter, you wish to have a linear phase filter. So this one called the linear phase, right? The phase is linear. So the message here is, it is important to have linear phase filter. Okay, so this is LP. All right, and that's really the thing here. So you say here, this is amplified frequency component, amplified frequency, and this is the part that would delay a frequency. I would say a frequency component in the signal. Right? A signal, any signal can be decomposed in different frequency components, and that for that particular input, the output can amplify and get delayed by these two. Okay. And that's why we need to have a linear phase. So the question, how can we design a system with linear phase? Right? That's what I would like to have. So maybe look at some examples and see what do we have. Okay. Example now and study. So take an example now. So I'm going to study a simple filter Hn, which is 1/2, 1/2. And this is the origin. If I tell you to implement this system, can you describe the input? What does it do? I filter a signal with that filter. Just take a sample xn plus xn minus 1 and divide by 2. Right? Just taking the average. Right? Taking the average. And let's see what this filter is doing to our signal. And I want to take the average, right? And intuitively, early on we see that doing this average, you can do more, but I just put 2 here. Seem to have an effect of smoothing out the signal. But now I want to see really why. Okay, so to do that, then, well, we need to go to the Fourier domain, because filtering becomes multiplication or having something like that. So the edge of omega is equal to, by plugging the formula, 1/2 plus 1/2 e j omega. Okay? And we need to find out this, so it is just these two things. Maybe I pull out E. The trick when we get to this, I want to find out something like, I want to represent it in this form, something of a real number multiplied with Ej to a complex, some real number. Right? I want to represent them in this phase and magnitude. Okay. So that is what we thank you. So that's what we're trying to do. You see, I give you something like this alone. It still doesn't tell you much about the system, right? Because you see, we need to know the phase and the magnitude. Okay, maybe I should put here some words here. So this is, the name here is the magnitude, and this thing here is the phase. A filter, when we talk about the filter, we're not just talking about this, we talk about the magnitude and the phase of that filter, because it's important as I described it. Okay, this and the trick to do is I want to make them in that form. Then I have this thing here. So this is 2 pair of complex number, and you know that when you add, remember if you have, so put it here, recode that if I have 1/2 Ej theta plus E minus J theta, what that give me? Cos of theta. Cos of theta. Okay. So that is, so I want to really play around with this so that I have something that I can get a real number out. Okay. So that's my play. And to do that, then you see the trick now is you want to factorize so that this thing is